Hello, everyone. My name is Miquel Martí, and I'm an industrial PhD student with KTH, Royal Institute of Technology, and universities, both in Stockholm, Sweden. And today I'm going to be talking about this work that we did with Sebastian Buivit, Alessandro Pieropan, Hossein Azizpour, and Atsu Tomaki. And this is really about how data is presented during the training of semi-supervised in semi-supervised learning. So first, how data is presented is really how one is sampling mini batches from the whole training set. And first, I'm gonna just introduce the basic approach that is the most commonly done in basic supervised learning, and then we'll see how that differs from how it's done in semi-supervised learning. So when you do mini batch sampling in basic supervised learning, you just select a number of samples B from the whole training set, and you usually typically assume that all samples are equally likely to get selected, so you are doing uniform sampling. So I'm gonna just quickly show how that looks in this toy data set, this 2Moon data set with two different classes, the red and the blue. So you select here we are highlighting just a bunch of these samples with these circles, and you just select some of them randomly. All of them are equally likely to get selected. So the differences in how this looks when you move to semi-supervised learning, I'm going to try to explain those. So first, here I'm showing the same data set, but where we dropped most of the labels. We just kept 6 labels for each of the classes. So all the labels all the samples that are in gray don't have an associated label. And in this case, we're in front of a semi-supervised learning problem. And Van Engelen and Host define semi-supervised learning as the branch of machine learning concerned with using labeled as well as unlabeled data. And very importantly, usually the unlabeled data is much more abundant. So we have much more unlabeled samples than we have labeled samples. And that's typically because labeling data is costly. And sometimes it involves human annotators, and sometimes it involves expert human annotators that are even more expensive to obtain. So if we follow the same sampling approach that we used in the basic supervised learning, we end up with something like this. Here, I'm just going to pass some possible samplings. And you can see that the number of labeled samples that are selected in each mini batch basically is a random quantity, and very likely very few samples in each mini batch are going to be labeled. So this is just because we're uniformly sampling from the whole training set, and basically we're going to be following in each mini batch the statistics of the whole training set. So if we have few labeled samples in the whole training set, we're going to have few labeled samples in each mini batch. However, what is most commonly done in semi-supervised learning is to sample separately from each of these two subsets of the whole training sets, the labeled set and the unlabeled set. And when you do that, you are putting a certain number of samples that are labeled in each batch, and a certain number of samples that are unlabeled in each batch. However, that comes with a side effect, which is that you are effectively oversampling the labeled data, since you have to repeat the same labeled samples over and over, since you have fewer of them. So let's look at how that looks in the toy problem that we showed before. Well, we just see that in each mini batch we have the same number in this case of labeled samples and unlabeled samples. So yeah, this is what we're going to be discussing today. So I mentioned that the second approach that I showed was the most common approach in semi-supervised learning, but there doesn't seem to be a good reason for it, or at least it has not been justified, and in many cases not even reported in the previous past works on semi-supervised learning what was actually done regarding mini batch sampling. And if we look into the literature of the past 10 years-ish, most of the works do not mention this. Sorry, most of the works use the oversampling of the label data approach, but some of them, only these 3 works identified here, also use the uniform sampling. And it is in those 3 works where there are some hints at why one or the other approach can be better. For example, in temporal ensampling by Laine et al., they mentioned that guaranteed stratification of labeled inputs might improve convergence while they use the basic uniform sampling approach. In Mean Teacher, they use both. They had experiments with both of them, just different experiments, one with oversampling of labeled data and one with uniform sampling. But they mentioned that when they did the oversampling of labeled data, that was an important thing to speed up training. And finally, in the work by Arazo et al. In 2020, they show that when setting a minimum number of labeled samples in each mini batch, they effectively reduce confirmation bias. So our motivation to do this is first to be able to understand why this oversampling of labeled data is such a common approach. And we believe that if we understand how, if that really actually helps, how it does so, because that can open some doors to designing more efficient semi-supervised learning methods overall. And finally, we have identified some issues when trying to apply this oversampling of labeled data approach, for example, in multitask semi-supervised learning. And I'm going to expand in the next slide, but we need to find alternatives to that. And for example, uniform sampling would be basically the most basic alternative that one can find. So I'm going to illustrate why there is issues when you try to do this separate sampling approach for different sets with this multitask learning problem with 2 tasks. Here we have a problem, well, we have a data set X, and we have a bunch of labels, a bunch of samples that are unlabeled for both tasks. So they have no labels for either task. And we have these 2 circles representing the samples that are labeled for one task and for the other. And there is a small subset that is labeled for other tasks. So in the end, we have 4 different possible configurations of the samples based on whether they are labeled for one task, another task, or both of them, or none. If we follow, well, a possible extension to the separate sampling approach would be to sample separately from each of these subsets. And that ends up with mini batches that have 4 different parts, one for each of these subsets. The size of these subparts is going to be basically a hyperparameter that we have to tune and would be regulating the rate at which these different samples in each of these subsets would be appearing during training. This is only with 2 tasks. If we go to 3 tasks, and we would be seeing 8 different subsets, and this grows exponentially with the number of tasks. So one can see that that's not a very promising approach for if we have this class of problems. So the goals in this work were first to emphasize the importance of the choice of mini-batch sampling approach in semi-supervised learning, and then analyze the differences between these 2 sampling approaches that I presented, and both in terms of the final performance and the training dynamics, and understand how this oversampling labeled data improves the results, if it does. It's kind of a spoiler here, and under which conditions that actually happens. So in order to do so, we ran some experiments in semi-supervised image classification with the Cypher 10 and Cypher 100 data sets. And we used fixed match as our semi-supervised learning method. And also we compared to strong supervised baselines. So for the ones that are not familiar with fixed match is like this semi-supervised learning method that combines pseudo labeling and consistent regularization, that are kind of the 2 biggest trends that have been very promising in the last few years in semi-supervised learning. And what it does for the labeled examples is just the basic supervised loss. In this case, it's classification problem, so we have a entropy loss. And for the unlabeled examples, it uses, I'm going to explain with this diagram here. It uses two different views of the same input. One is weakly augmented and one is strongly augmented. And from the weakly augmented, we get a prediction. And if the confidence is over a certain threshold, we obtain a pseudo label. From the strongly augmented version, we obtain a prediction and we use it to train against the pseudo label as the real target with the same cross entropy loss that we have for the supervised loss. So let's look at the results. Here we show results for different amounts of labels, and we compare, as I mentioned, also with the strong supervised baselines. And when we do so, we see that both the oversampling label data and the uniform sampling approaches outperform using only the supervised baselines, which is good because it shows that uniform sampling can also be viable if oversampling is not possible. But we can also see that oversampling does indeed outperform the uniform sampling. And also, however, we see that that depends a lot on how many samples we have labeled and also how long of a training do we allow. When we have more labels or have longer trainings, the gap between performance between both sampling approaches is greatly reduced. So let's look at the training dynamics. Here I'm showing different quantities that we can compute over training for the Cypher-10 experiments with 250 labels in red and 4,000 labels in blue. We'll focus on the 250 labels because it's a bit more extreme, so it's easier to follow. And the solid lines show the oversampling label data approach, and the dashed lines show the uniform sampling approach. So looking first at the uniform sampling approach, we see that with few labels, the uniform sampling is extremely inefficient early in training. The training error goes down very slowly for basically the first 10% of the whole training that we allow. And the loss, the supervised loss also doesn't go down. And basically that means that the confidence of our predictions remains very low for a long time. And that doesn't allow these predictions on the labeled data to be used as pseudo labels. So it doesn't allow to have any semi-supervised loss. So we have no loss on unlabeled data. And basically we're not using the unlabeled data at all. In contrast, when we do oversampling, the training error goes down very quickly early on. And the confidence of the predictions on unlabeled data go up quickly as well. And the ratio of samples in each mini batch that are actually used as pseudo labels goes up also much quicker, and so does the semi-supervised loss that I'm showing here. So some conclusions: oversampling label data does improve learning efficiency early on. However, in terms of final results, more labels or longer training close the gap between both sampling methods. But overall, the take-home message, at least for me, is the uniform sampling is still viable, which opens the doors to use it directly in, for example, semi-supervised multitask learning problems. Some lines of future work that I wanted to mention. First, this was work only doing an analysis and showing results on fixed match. So methods that are substantially different from it might behave differently, and it would be very interesting to see what happens in those. So that would be methods that are not using pseudo labeling or are not using consistency regularization. And more interestingly, we are interested in finding methods that improve the learning efficiency overall. And we believe that exploring other mini-batch sampling approaches can be a very interesting line of research to do so. And it's especially interesting for multitask learning. But also multi-phase training schemes, such as first pre-train in a supervised or sub-supervised way, and then do some other training, can be an important part of finding overall a very efficient way of learning. So thank you, that's all. And here is the link to our preprint that we posted on archive. And I also want to thank the funding of the Swedish Research Council and BASF.